Hello and welcome to Flip Academy. Today we're going to be looking at the first part of the differentiation in your paper 1. So if we have a think about, first of all, what is differentiation? So normally when we're talking about differentiation, it's always talking about the gradient of some kind of graph. So before, when you had like a graph that may have looked something less crooked than this, but whatever, right? What you'd do is you'd have 2 points. Let's say this was 4 and 16, for example, and this was 1 and 3 or whatever. What you'd do is you'd find the change in the y and you divide it by the change in the x and you get a gradient, right, which is perfectly fine. And then if you had a curve, for instance, so let's say you had something like this, if you wanted to find the gradient, let's say at this point, you'd have to draw a tangent and then you'd have to find the gradient of that tangent. There is a problem with this, right? First of all, is that if you draw a tangent and calculate the gradient of that tangent, it's always going to be an estimate 100% of the time, because it's not accurate, right? It depends on how you draw the slope and all of this other stuff. Also, it's really, really inconvenient if you have to keep drawing these tangents if you want to keep seeing how the gradient's changing over time, right? What about the gradient over here or over here? So, Isaac Newton kind of came up with a way of working out an equation for the gradient, and that is differentiation. Okay, so differentiation is all about rates of change. So rates of change. Okay, so all I'm going to be asking myself is how quickly y changes with x. Okay, that's all it tells me. However, y and x are just variables, right? So I can actually say that this is any two things. So I could say how quickly volume of water changes with time. I can say how quickly distance changes with time, which would be speed. I can say how quickly speed changes with time, which would be acceleration. You can ask yourself all of these questions. And this is actually going to come up a lot in the mechanics section as well. Okay, because, and again, if you do physics as well, that kind of stuff. But this is actually revolutionary, this kind of stuff. So it's really, really, really important. So all we're going to be asking ourselves is how quickly y changes with x. So in this case, it's going to be how quickly, in this case, the y coordinates change with the x coordinates. But keep in mind that some of the questions, well, one of the questions later on, it is going to use the fact that it can be any two variables. It doesn't matter which one it is. Okay. Now we have to talk about the notation. Okay. So in this notation, we have dy by dx. And that represents the first differential. So that means we have differentiated one time. And if you look, when we use change in y over change in x, that's delta y over delta x. That is the exact same as saying dy by dx. Okay, so in fact, the delta is actually the Greek letter that represents d. So this is actually 100% accurate here. However, this can also be represented by using an f with an apostrophe, an f prime. Okay, you also have d squared y by dx squared, which is the second order differential, is normally what we say, but we can just say second differential, which is represented by f two apostrophes. Or they call this f prime and f double prime. And you can keep going, by the way. You can go to d cubed, d to the 4, d to the 5, whatever. Okay, but this first spec point, all it's asking you to do is to understand that the gradient of a curve at a point is going to be essentially a limit of these tangents. So I haven't actually told you what differentiation does. Essentially, it does draw these tangents for you, but it makes them, each point here, infinitesimally close to each other. So what that basically means is you have tangents at every single coordinate, which of course there's an infinite number of coordinates along this curve, and it makes an equation for you. So it mathematically does it for you, which means it's going to be perfect rather than your, by hand using a ruler kind of way of doing it. So this spec point just simply asks you to know what that is. Okay, so to know this notation. Other than that, we're completely done with it. Now we need to use the derivative of x fab n together with constant multiple sums and differences of functions and of composite functions using the chain rule, and then apply differentiation to gradients, tangents and normals, increasing and decreasing functions and rates of change. that was a hell of a lot of stuff. So first of all, use the derivative of x to the power of n. So if you have y equals x to the power of n, I'm actually going to write ax to the power of n, so with some letter in front, some number. When you differentiate, it's super easy. You keep the a the same if there is a number in front, then you times it by the power that it currently has, and all you do is you reduce the power by 1. That's it. So you bring the power forward, reduce it by 1. So let's have a look, right? Let's say if we had y is equal to x to the power of 4. Okay? Then dy by dx is I bring the power to the front and I subtract 1 from the power. That's it. Not too bad, right? And if we had like a number in front, let's say 5x to the 6, then dy by dx is just bring the 6 forward, so we get 5 times 6, which is 30x, reduce the power by 1. 30x to the power of 5. Nice and easy, right? Simple stuff. How about composite functions? So that's actually what we're going to look at right here. So I'm not going to go through it, I'm just going to show you what it means. And I'm going to tell you how to do it because in my opinion, the actual equation is a bit, it's a bit difficult to kind of read, right? So instead we're going to be using what the chain rule is. So the chain rule, all it states is if you have a function that has some kind of power, right? So it could be something, let's say, like x plus 2 to the power of 10. Okay? All you do is you differentiate what's inside. So in this case, x is to the power of 1. So I bring 1 forward, that gives me 1. And then x to the power of 0, which is also 1. So we just have 1 out the front. I then bring the power forward, which is 10. I then write the same bracket again, but I reduce the power by 1. So it's just 10 x plus 2 to the power of 9. Okay, that's all we have to do. So why does that apply to this question? Well, if we have a look, we have a fraction. Now, you can't really differentiate fractions. What we're going to do is, using indices, we're going to bring this upwards. So we have y equals 12, 3 minus 2x to the power of minus 1. And now when we differentiate, here's what's going to happen. The 12 is going to stay exactly where it is. The next thing we did is we differentiated the inside. So one thing to note about differentiation is constants go to 0. So if I have y is equal to 4, dy by dx is 0. And hopefully this makes sense, right? If think about it, if I had a line where it's y equals 4, what's the gradient? 0. But also think about it in terms of differentiation now. How quickly is y changing with x? Well, y doesn't change. So it's 0, it's not changing at all. Okay, so there's some things to think about. So I differentiate the inside, it's 0, then I get minus 2. Okay, so times it by minus 2. Then I bring the power forward, so times by minus 1. Then I write the exact same bracket again, and I subtract 1 from the power. So this leaves me with 12. So minus 2 times minus 1 gives me plus 2. Plus 2 times 12 gives me 24. 3 minus 2x to minus 2. So again, take it really slowly if you haven't seen that before. Make it super clear in your mind. Go through it one more time. The chain rule it's not bad. It helps a lot, makes things a lot easier, and in my opinion isn't too difficult, and they can't really ask you to do anything too tricky with the chain rule. Okay, so don't worry too much about that. However, this is where things get a little bit more interesting. So a point moves along this curve. As the point passes through some coordinate A, the x-coordinate is increasing at a rate of 0.15 units per second, and the y-coordinate is increasing by a rate of 0.4 units per second. So here, this x-coordinate thing is we have the change in x, but the question is, what is the variable on the bottom? Well, it says per second. So this is actually by dt, where t is time. Okay? So again, that might be something you haven't seen before. And likewise, it's increased at y-coordinate, so dy, it's increasing, so again, that's why I've made it positive, at 0.4 units per second. So again, just to go through this to make it super clear, is we're taking the x-coordinate and dividing it by some amount of time, which is where we get the per second. So that's why we have dx by dt. we have the dt because it says per second. If it said per meter cubed, then I'd write dv for volume. If it said per kilogram, I would write dm for mass. If it said per newton, I might put df for force. Okay, so that's how I knew it's dt. Okay, it's literally the fact that it just says per second. That is the only reason why I've put it there. Okay, now the thing is, it says find the possible x coordinates of a. Now we only have dy by dx. Now here's where things get a bit funky, and you probably won't know to do this unless you are unless you've already done it before, right? So I want dy by dx because that will give me an equation I can solve. So how can I manipulate these two fractions to give me dy by dx? Well, what I would like to do is do dy by dt. I need to cancel the dt, so I would need to times this by dt, and I'm left with dx. Now that's the same as doing dy by dt divided by dx by dt. Because remember, when you divide fractions, you flip the second one and change to multiply. So again, you probably wouldn't know this unless you've done it before, but dy by dx is just dy by dt divided by dx by dt. And it's the same no matter what this bottom thing was, if it's dm, dm, or df and df, or dn and dn, whatever the hell it is. So we have 0.4 divided by 0.15, so you could use your calculator, or you should know it's 8 over 3 that should be. Like that. So we have dy by dx is equal to 8 over 3, and we also know that dy by dx is this thing, which can also be written as 24 over 3 minus 2x squared. Again, if you remember your rules of indices, so with differentiation and integration, which we're going to cover a bit later, it's a mix of basically everything you know. It's indices, it's algebra, you're going to be using partial fractions, you're going to be doing all sorts of stuff. So what we have here is we have 24 over 3 minus 2x squared is equal to 8 over 3. Let's scroll down a bit, give us some room. I'm going to once again do cross multiplication, so times both sides by 3 minus 2x squared. Actually, before that, I'm going to divide both of these by 8 to make it a bit easier. But I'm going to cross multiply now, so 3 times 3 is 9 equals 3 minus 2x squared. So again, all I've done is I've times by the denominators of both of these things. So times both sides by 3 and times both sides by 3 minus 2x squared. Expanding the brackets on the right hand side will give us 9 plus 4x squared, and then it's going to be minus 6x, which is minus 12x. So you might notice that these two will cancel out, so we have 0 equals 4x squared minus 12x. So the cool thing about this is that we can actually just factorize this and solve it. We don't need to use quadratic formula or anything. We have x minus 3 equals 0. So we have x is either equal to 0 or x is equal to positive 3. And since it actually does say find the possible coordinates of A, we don't need to specify which one it is. And to be honest, we wouldn't be able to tell anyway, because there's no other information available. Next we have the point P lies on the curve with equation y equals 3 over 2x plus 1 with x coordinate 1. Find an equation to the normal to the curve at the point P. So here again it's a fairly similar way that we've been using kind of gradients before. If you remember, when you have equations to normals, you do the negative reciprocal. We're going to do the exact same thing here, so you don't need to worry about it. So we have some curve and there's a normal, a perpendicular line to it. So we have part A here. Again, we're going to write this in terms of indices. So why do I know that I'm going to differentiate other than the fact that this is a differentiation video? Well, besides getting meta, the reason why I know is because whenever we talk about equations of normals, we need to find out the gradient of the actual curve, right, or the line in most cases. So what we have to do here is work out the gradient of the curve when x equals 1. And that will give me the gradient that I'm going to take the negative reciprocal of. So first thing we do is differentiate. So So again, the 3 stays exactly the same. Differentiate what's inside the bracket, so that would just be 2, because the x goes away. Then we take the power, which is minus 1, which is now 2x plus 1, and subtract 1 from the power. So that leaves us with minus 6, 2x plus 1, minus 2. Not bad. The next thing it tells us is that x is equal to 1, right? So we need to sub in x equals 1. So this is how the actual differentiation formulas work, right? So what we've got here is we've got an equation for the gradient that only depends on x, right? So whatever our x-coordinate is, this will now give us the gradient. So when x equals 1, we have that dy by dx, aka the gradient, is equal to minus 6, 2 times 1 plus 1. And honestly, if you wanted to be a bit lazy, you can actually just, factorize this out. But let's do it properly. We can use a calculator for this one. So we have minus 6. And again, technically speaking, you could work this out in your head or do it another way. But let's just be a little bit lazy. Minus 2/3. Okay. Now, there is something else that we need to know, is we should know what the y-coordinate of point P is. So when x equals 1, we also have that y is equal to 3 over 2 times 1 plus 1, which is 1. So the coordinates here are just 1, 1. That's quite easy. So it says find an equation to the normal to the curve, or it should be of the normal to the curve at the point P. So now if we actually work out what the normal is, the gradient is going to be the negative reciprocal of that, which is 3 over 2. So now we have y is equal to 3 over 2x plus c. Now we're going to sub in the fact that x is equal to 1, and y equals to 1. So we have 1 equals 3 over 2 times 1, which is 3 over 2, c. So c is just equal to negative a half. So my equation for y is 3 over 2x minus a half. That is all we need to do for that question. So again, hopefully not too bad. Hopefully. It now says the normal intersects the curve again at point Q. Find the exact coordinates. So the only way to do this, and hopefully you know this from the previous videos, coordinate geometry and stuff. If not, you should go back and check those out. All you need to do is equate this equation of a line with this equation of a curve. So let's do it. So I'm going to write out the equation of the line first. And again, keep in mind that we should actually get a quadratic, right? Because it happens twice. So we should actually get something that has 2 solutions. And that's 3 over 2x plus 1. Yeah, we could multiply it through by 2. There we are. And this is just to make the algebra a little bit easier on my weak and weary bones. Okay, so now we're going to multiply both sides by 2x plus 1. And we have this one. So then here we have 6x squared minus 2x plus 3x, that's plus x. And minus 1 equals 6. Let's split this in half so we can go back up here. Move it all over to one side, we have 6x squared plus x minus 7 equals 0. So to factorize this, again, you can use the quadratic formula. Don't feel like you need to factorize, but again, if factorizing is easy for you, then why not do it, right? So that should be, so this obviously should be x. We're going to have a minus 1 here because it needs to be negative of some kind, which means this has to be a plus 7, which works out perfectly. So we have either x is equal to negative 7 over 6 and x is equal to 1. So we should keep in mind that the x equals 1 is point P, isn't it? Because that was our equation here. So the exact coordinates of Q would be this solution here. So when x equals minus 7 over 6, y equals 3 over 2 minus 7 over 6. Right. And I don't know about you, but I'm definitely not going to work this out in my head because I don't want to. So we have 1.5, and hopefully it gives me it as a fraction. Minus 9 over 4, perfect. So just to write out our answer, I barely gave myself enough space for this question. Our answer is this. This is Q. Okay? So, for the next question, we need to be able to locate stationary points, determine their nature, and use information about stationary points in sketching graphs. So this first part we're actually not going to do because this is integration. Okay, but I needed it to kind of demonstrate the question here. So, stationary points. What are stationary points? Okay. Stationary points are anything where the gradient equals 0. So you would have come across these potentially in GCSE maths where you had to use completing the square to find stationary points. So in this case, it's just anywhere that dy by dx equals 0. Now dy by dx you do actually find out in the first part, but again that's integration, so it's not in this. So I'm just going to tell you what the equation would be, and when we come on to do integration we will go back through this expression. Okay? It'll be this. And they tell me that there's one stationary point at 3, 6. So we need to find out the other one. So again, this is where the gradient equals 0. So anytime you see like a hump, so a maximum, you also have a minimum at the bottom, and you also have something called a point of inflection, which I'll draw out for you in 1 second when we do the last part of this. So let's get to it. Finding the x-coordinate of the other coordinate, so all we need to do is when there's a stationary point, it's always going to be equal to 0. So we just need to equate this to 0, then all we need to do is factorize this, so we should have x minus 3, x minus 2 would do it. So we have x equals 3, x equals 2. However, if we look back here, we already have the 3 one, so this is our answer here. Okay, so nature of the stationary points. Let's actually talk about this, shall we? We have 3 types. We have a maxima, which you've probably already seen before, which is where it will have a peak. Keep in mind, I'm going to be drawing a lot of quadratics, but keep in mind that anytime you see a hump, counts as a maxima. So for example, if I had something like this, this is a maxima. Okay? It's not actually the biggest value because these are called local maxima, so it's where you have a peak locally. The next one you have is called a minima, which is this one. Okay? So it's where you have a trough, as we might call it. So again, that would be the U shape if it was a quadratic. The last one we have is something called a point of inflection. Sometimes called a saddle point, but saddle points are actually for 3D graphs, not for 2D ones. So point of inflection actually looks something like this. So I'm actually going to draw this slightly higher than it should be. Okay. So, what is the difference? Why do we care? And how can we tell the difference as well? Well, those are all very good questions. A maxima is specifically when the gradient goes from positive to negative, right? Here the gradient goes from negative to positive, and here the gradient goes from positive to positive. You can also have negative to negative, and you can kind of think about how that would work. It would basically be the inflection of this, right? So like that. So either way, right? And the reason why these are important is because most coordinates on a graph are actually boring. We don't care about them, right? Like all of these coordinates here, they're all the same, they're all the same, they're all the same, they're all the same, right? But the idea here is that it goes from positive and then it's negative here. There's a point in between where it equals 0, where it's completely flat, right? An infinitesimally small point, but it still exists. And likewise here, there's a point where it goes flat, and here it goes flat as well for a very, very short period of time. So the question is, how do we know how to do this? Well, first of all, at these points, the gradient's always equal to 0. So dy by dx doesn't help us here. dy by dx tells us that there is one of these 3 points, but it doesn't tell us which of the 3 points it is, a maximum, minimum, or point of inflection. So, how do we determine the nature of them? What we do is we take the second order differential. We look at d squared y by dx squared. Okay. Now this is where things can get a bit kind of complicated. It's basically backwards to what you'd think, right? So what do you think it would be for a maxima for this? You'd probably guess that it's greater than 0. But judging by the tone of my voice, you can probably tell it's not. For the maxima, it has to be less than 0. Now, I'm going to explain why this is, but it's honestly not that important to know. The reason for this is because this is telling me how quickly the gradient is changing with respect to x. Okay? So if you remember, when dy by dx is positive, it means it's going up. If it's negative, it's going down. If it's 0, it's going across. This thing here, all it's telling me is how quickly the gradient is changing with respect to x. The reason why it's negative is because, look, the gradient goes from positive to negative, which means the change, the acceleration of the gradient, has to be negative because it's going from positive to negative. That's why it's less than 0. Because the rate of change of the gradient has to be negative for it to go negative, right? If you think about it in a car, right? If you're accelerating, your acceleration's positive because your speed's going up. If you want to slow down, your acceleration has to become negative for you to decrease. Same thing here. For the gradient to decrease into the negatives, you need to decrease the rate of change of it. It needs to be negative. So for the minima, it's again the opposite of what you might expect until you know better. It's greater than 0. For a point of inflection, you can actually guess what this is. If we already have positive, negative, what about when it equals 0? And that is indeed what positive point of inflection is. So if you look here, it goes from positive to positive, so the overall change is nothing. It's the same. And the key point here is that both of these sides have the same gradient. Okay, they're actually, it's completely symmetrical, which is cool. Well, it's not symmetrical down the middle, it's symmetrical. You know what I mean. So, this is a 2-mark question. You obviously don't need to do all of this. Let's have a look. We need to determine the nature of each of the stationary points. So what I'm going to do is write down what d squared y by dx squared is. 2x minus 5. Nice and easy peasy. And we need to determine the nature of both stationary points. One stationary point is when x equals 3, so let's do that. It's greater than 0, which means it is a max, I'm joking, minima. It's a minima, because it's positive. And then when x equals 2, what's the other one? Yep. We have d squared y by dx squared. You can probably already see what this is going to be. A maxima. Okay. Generally speaking, we're only going to be dealing with 1 or 2 stationary points, but keep in mind, like, depending on how big the graph is, like, funnily enough, for example, if you think about sine and cosine graphs, they go on forever, so you'd actually have an infinite number of stationary points. But there are certain graphs that have, like, multiple, right? So when you have a cubic graph, you have 2 stationary points. When you have a quartic, you can have 3 stationary points. If you have a pentic, so to the power 5, you can get 4 stationary points, and so on and so forth. But that's everything you need to know for the first part of differentiation for paper 1. So I'll see you in the next one.